We now turn our attention to common modifications in the basic inverting amplifier circuit. By replacing the resistors in the feedback and the source with capacitors or combinations of resistors and capacitors, the differential relationship between current and voltage in a capacitor allows us to implement integration and differentiation operations. In other words, we have I is equal to C dV dt, and we also have V is equal to 1 over C times the integral I of t dt plus the V sub C at 0 plus the initial value of the voltage. We can also look at it from the frequency perspective, and the frequency-dependent nature of Z sub C now makes the gain of the amplifier a function of frequency and opens the door to using amplifiers as active filters, or filters that provide gain in the pass band and more aggressive attenuation in the stop band. Using the same technique of summing the currents at the inverting terminal, we can derive the gain in terms of the generalized impedances Z1 and Z2. Thus, the gain term V out over V in is equal to negative Z2 over Z1. Here we note that the gain term, because the impedance of a capacitor, Z sub C is equal to 1 over J omega C, or in the Laplace domain, Z sub C is equal to 1 over C times S. This gain term now actually becomes the transfer function T of S. T of S then is equal to negative Z2 over Z1. And we can also talk about the frequency response, or T of J omega, which is equal to T of S evaluated at S equals J omega. Thus, the gain of the amplifier, when we have impedances present, becomes a function of frequency. It's no longer effectively constant over the frequency, as we've seen when using simply resistances in the circuit.